to AP Calculus. We're on the last page of the handout entitled First Fundamental Theorem. Now, we've been working a lot with the fundamental theorem verbally. We've looked at, in general, this idea of final equals initial plus net change, not total change, but net change. We're going to take final what? Final position, final velocity, final acceleration. Let's find out. Let's read the problem. The acceleration of an object moving back and forth in one dimension along a straight line, we call that rectilinear motion in physics, is given in the graph below. Zoe, were you here in class today? We did. No, you were. Have you done this problem yet? Yeah, you have. Okay, so that was a little bit of a difference between fourth period and seventh period that day. So you can be a resource for your group. But they're telling us that the velocity of the object at time 3 is negative 35. Find the velocity at time 18. Okay, so they want final velocity. You'd be amazed at how much your thinking process is assisted by words. Thinking uses words. So to get the final velocity, we're going to have to take the initial velocity plus the net change, not the total change. If it were total change, then any negative velocity would have to be flipped over to positive velocity. We want the net change. Delta is a symbol that represents change, a triangle, change in velocity. So they're asking for V velocity at time 18. So I believe our initial velocity, which is given as the velocity at time 3, plus, can someone give me some mathematical symbols I can use to represent the net change in velocity? V of 18 equals V of 3 plus what? Well, take a few moments to think about what the analytical representation, the symbols, the calculus symbols would be that you would use to represent net change in velocity. Just give that a go. I'm going to pause the camera while you wrestle with that. Back. I'm seeing a lot of people use the integral from 3 to 18 of v prime of t dt. That's the same thing as acceleration as a function of time dt. So there it is. You can use either one, either v prime or a. Any questions on how to do the setup either verbally or analytically? Just turning the camera so the choice bits get included. Okay. Now, in the past, we've given you either a function for a of t, like an equation for a of t. Didn't give you that this time. Sometimes we give you a table of values so that you can approximate this net change in velocity using a Riemann sum. Didn't give you that. This time we're giving you a graph. College Board says that you should be able to evaluate a definite integral or approximate a definite integral based on an equation, a table of numbers, or a graph. So here we go. We got to get from 3 to 18. So we're going to remember our geometry skills for finding areas of trapezoids, rectangles, triangles. So there it is. Take some time to find not the total area, but the net area by doing the right thing mathematically with area 1, area 2, area 3, and area 4. So once again, I'm going to pause the camera while you do some geometry to approximate this net change. And does anyone have any questions as to what the expectations are to find V of 18? Yeah, Jeff.
What's the number after that?
Yeah, that should be a 12 because it's got this 12, 10. So that's really a 12 right there. Okay, any other questions as to what the expectations are? Okay, you can pause the camera, you can give that a go. You've had a chance to wrestle with this. You might have forgotten what the formula for the area of a trapezoid is. The basic idea is that you take the average of the bases times the height. I like to think of the height in this situation as being 3, and then one base is 7, the other base is 10. Off camera, we had a brief discussion about how to get the equation of this line. I just set up the point 0, 4, and 6, 10. get the change in y is 6, y2 minus y1 is 6, x2 minus x1 is 6. So I observed that the intercept was 4, the slope was 1. So using the equation y equals 4 plus x, when x is 3, I can tell that y is 7. So if I take base 1, which is 7, plus base 2, which is 10, divided by 2, that's the average of the bases times the height. Horizontally, the height is 3. So that's the area of the trapezoid plus, that's area 1. Area 2 is a 6 by 10, so we'll call that 60. Area 3 is 1/2 base times height. I'm going to continue on here, wrap around to the next line. 1/2 times 15 minus 12 is a base of 3 times the height is 10. Now, here's where it gets tricky. Since that's going to be a negative area, do I keep it negative or do I change it to positive to get net change in velocity? Which do I do? Do I allow that to be a negative number, or do I multiply it by -1 to make it positive? I'm getting thumbs up on negative. Yeah, because it's net change. It's kind of like if it were final position equals initial position plus net change in position, that would be, it's like, that's how you find displacement. It's final minus initial. So yeah, we're fine with the negative number. So we're just going to take 1/2 base times height, where the base is, that's 18 minus 15 is 3. And we're going to think of the height as -8. So of course you do have to simplify all this, but assuming that once you get the setup, you can simplify it accurately and put the answer on are we in feet per second? Yep, so we expect that the velocity at time 18 will be this number of feet per second. So that's the warm-up question. We're doing calculus in the spirit of the vegan tomorrow approach. It's something that College Board preaches. They want you to understand calculus verbally, graphically, algebraically, numerically, with technology and how it's connected to the real world. Any questions on the warm-up? Alrighty. One concept that we've touched on a little bit, but I haven't taken the time to go fully in depth. There's a difference between people and animals that's seen in a calculus class. Now, just to confirm, is it true that we have not yet had the spherical chicken talk? That's true? Okay, I just want to make sure, because sometimes I sneak it in to lessons, but did we have that little talk about how when someone asks you to solve the equation 3x plus 1 equals 11, that's a mistake to say that x is 10/3? Did we have that talk?
No, we did.
We did learn from
Let me
that.
refresh your memory. When in fact, in my pre-calc advanced classes, back when I taught pre-calc advanced, this is the first equation I would start out with at the beginning of the year. I'd say solve the equation 3x plus 1 equals 11. Students would say, oh, I know x is 10/3. Correct answer is, does anyone remember the correct answer? The correct answer is x is undefined. This problem is meaningless. See, if x represents a number, then 3x can be interpreted as multiplication. But sometimes people say, I'm going to go to college X and study field of study Y. What does 3 times Northwestern University mean? It's meaningless. If x represents a real number, if you attach meaning to words, or if you attach meaning to the symbol x with words, if you say let x equal, or let it represent a whole number, now x has meaning. If x represents a whole number, then what's the correct answer? No solution. There are no whole numbers that make this equation true. We can say no solution. What if we attach a different meaning to x using words? What if we say x represents a real number? Then what's the solution? Then we can say 10/3. The moral of the story here is that LMBY, let meaninglessness bother you. Every symbol in mathematics should have meaning attached to it. Every child should have a name. If you have something in a word problem, say someone's shadow, just right there, it's like, come on. Attach meaning to that, say W represents the length of the shadow. You can do it with words or with symbols. Animals can't do this. This elevates the status of human beings when you realize that you do something by just saying let X represent a whole number. You're doing something that Bonnie and Clyde cannot do. These are my dogs. Adam, go ahead.
What about if a question says find X and you solve for X? Is that not right because it doesn't say let X represent something?
Well, let's see what happens on the AP test. On the AP test, they say the very first direction on the AP test is Calc AB. Unless otherwise specified, the domain of the function f is assumed to be the set of all real numbers x. They just do step one. Because you can't, they know that people don't have to do the test unless x is defined as a real number. They know that people can get a 5 by writing on every problem. The symbol is undefined, or this symbol is undefined, this problem is meaningless, this problem is meaningless. They don't want to give people a 5 for writing this problem is meaningless on every single problem. They want to attach meaning to symbols with words. Too often, Adam, in American math education, meaningless does not bother students, meaningless does not bother teachers, and they just answer questions in animalistic fashion as if it's stimulus response. If you see this, do that. Don't even try to understand it. Just get the right answer, and then you'll get a Jolly Rancher. Or if you don't get the right answer, you'll get some sort of punishment. That's how you train animals. That's not how you treat people. That's not how people are supposed to learn. Okay, so, yeah, this is kind of a big deal. It's like, what? No more sugar? So, friends, look at how animals attach meaning to symbols. Bonnie and Clyde are the dogs that I've noticed live in my house day after day. And they can attach meaning to symbols using their senses. I can teach Clyde what spherical is. Here's how I could teach him what this audio symbol spherical means. Spherical. What does that mean? I could bring out something that's spherical. I could say spherical. He would smell it. He would look at it with his senses. He could attach meaning to it so that if I hide the tennis ball and say spherical, it would come into his imagination. Yeah, because when I say walk, they get really excited. Why? Because they know what a walk looks like. Most of all, they know what a walk smells like. They've attached meaning to walk using their senses. If I were to bring out a chicken and say, chicken, 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 Clyde would smell the chicken. He would taste the chicken. And so when I say chicken, even if there's not a chicken there, meaning is attached to chicken in Clyde's imagination. So when I say chicken, it would pop into his imagination. Do you know why a spherical chicken could never pop into Clyde's imagination?
He doesn't have rational thought.
He doesn't have rational thought. Spherical chickens do not exist in the physical realm. They cannot be smelled and tasted or looked at. You know what a spherical chicken is because you can attach meaning to the phrase spherical chicken using words. A spherical chicken is a chicken that is spherical. Even though, they don't exist in the physical realm, but a spherical chicken is perfectly spherical. You put it on the grill, it's a real chicken. It has a heartbeat, you cook it up, put barbecue sauce on it, it's delicious. So, stay with me here. When I went through that, when you do Roman numeral 1, and you say, okay, I'm going to let X represent the length of the shadow, you're doing something that no animal can do. When an engineer imagines something that does not exist in the physical realm, they imagine, okay, maybe there's going to be a network of computers, or maybe there's going to be a bridge, and they represent it with mathematical symbols, and they bring it into existence from non-existence. You're doing something that no animal can do. Apes do not build libraries because they can only imagine things that they can sense. Even the beaver dam is not a work of engineering. It's stimulus response. If you put a beaver into a room with a tape recorded sound of running water, it's just stimulus response. They will take building materials and start building a dam even though there's no river. It's just a response to stimuli. It's front-loaded information. So When I was telling my students this, a student named Mackenzie, who made the spherical chicken posters right there in the back of the room, we'll put it on camera for those of you watching at home or while you're out jogging on the prairie path. That spherical chicken poster was made by Mackenzie. Why? Because, Cindy, she'd been told her whole life she was an animal. In school, the authority figure said, you're an animal, you came about by accident. You are an animal. You came into existence through purposeless, non-intelligent processes called evolution. And she came to math class, and she found out, wait, I can do something that no animal can do. Maybe I'm not merely an animal. And so not only did she make the poster, she made me a spherical chicken hat. She made spherical chicken stuffed animals for my children. And her self-image was transformed. As a mathematician, not only should you let meaninglessness bother you, you should recognize that every time you attach meaning to a symbol with words, you are engaging in a uniquely human activity that no animal can do. The next part of our lesson is the main part of the lesson today is the mean value theorem for integrals. And this is going to be on, there's a couple of things I want to look at before we get to the main part of the show. First of all, there is a homework assignment due today. I want to remind you that come Monday before school or after school for the first of 2 cumulative review sessions. But the homework that was due today, I want to let you know that my 4th period class had a request for me to explain what was going on with number 105 star. How many of you would like to hear me explain what was going on with problem 105 on the homework due today? Maybe it was clear. Okay, there is a request for explanation. This one was primarily a geometry problem. And let me grab the door. Remember back in Algebra 1 when they said things like the parabola y equals x squared has an axis of symmetry? Goes right down the middle, y equals x squared. So y equals x squared from -2 to 0, by symmetry, that area from -2 to 0 would be the same as the area from 0 to 2. That's just because of the symmetry of the x squared function. It can be reflected over the y-axis. So that's why the integral from -2 to 0 by symmetry is the same thing as the integral from 0 to 2. So just by symmetry, it's going to be 8/3. That's all that was going on there. How about from -2 to 2? Well, from -2 to 2, that's just 2 of the 0 to 2's. So that's why, by symmetry, we're not even using any special properties of calculus. We're just looking at it. This area from 0 to 2, which is given as 8/3 and could easily be calculated using the evaluation theorem, it's just the same thing as 2 of the 0 to 2's. This problem is designed to train you to prefer zeros as limits of integration whenever possible. On the third one, this is a property of calculus that we learned yesterday, and that is a scalar multiple comes out front. So 0 to 2 of x squared dx is given as 8/3. So that was one that was actually based on a property that we learned in class. And this last one is also based on a property that we learned in class, and that is that the scalar multiple comes out front. By symmetry, I can take 0 to 2 instead of -2 to 0. Yeah, so the first one's by symmetry, the second one is scalar multiple. So does that help with any of the confusion you might have had on that last homework problem? Do you have any follow-up questions? Yes?
Can you explain C again?
Part C again? Sure. So the request is that we look at part C again. And is it true that part C is this part over here? Somehow the C label, someone absconded with the C label. Oh, it's back. Thank you for returning that. All I'm doing here is treating this negative sign as a scalar multiple of -1. So it comes out front, and then I take the given information of 8/3 and multiply it by -1. Further questions on the homework due today? Any part of the homework due today would be fair game here.
Can you show us the graph again?
Yeah, the graph up here of y equals x squared, yeah, it's just the parabola y equals x squared from -2 to 2. Has two equal areas. This part's 8/3. This area is also 8/3. Okay, so that's one thing that I wanted to look at first. Another thing that, okay, we took care of that. So I think we're good to go with the new material. The new material is short. We've learned all the concepts that we need for calculus, the limit, the derivative, the integral, both the indefinite integral and the definite integral. So from now until the AP test, it's just applying the calculus concepts to real-world situations. And today's application is something I'd like you to record on a sheet of teacher supplied blank paper. So I'm going to pause the camera. Today's lesson is entitled, and you can write this on your sheet of paper, it's entitled The Mean Value Theorem for Integrals. The mean value theorem for integrals. We've looked at the mean value theorem, which is really for derivatives. This is the mean value theorem for integrals. It has an alternate name. It's also called the average value of a function. Okay. Now, what I've noticed over the years is that average value of a function questions show up on the AP test every year, and students confuse them with problems that are worded similarly. So I've decided to do, this is the first time I've decided to do this, 18th year teaching calculus, but I've gotten tired of students struggling with average value of a function question. So I've realized that I need to show students the problems that are similar to average value of a function, but different. The first one is, in fact, we're just going to call this problem 1 with 3 parts, A, B, and C. In problem 1, I'm going to hold off on the A until I give you the given information. In problem 1, I'd like you to consider a velocity function, v of t, kind of like in the opener question, except this time it's kind of a generic function. We're going to look at it from time 1 to time 7. So here we have some velocity function of t. Velocity could be measured in mph, miles per hour, time measured in hours. Now, question A. What is the instantaneous acceleration? Instantaneous acceleration at time 3. Okay, they're not asking for the average value there. Here they're just asking, hey, at time 3, what's the slope of the tangent line? That's how you would answer the instantaneous acceleration. You would say, what's v prime of 3? We could approximate it. It looks like, based on my picture, v prime of 3 might be something like 1/2 or something. So that's one question we could ask based on this given information. Question B, what is the average acceleration? Average acceleration over times 1 to 7. If this is a velocity function, maybe this is the velocity at which my wife is driving to work. At hour 1, she's at maybe 40 miles an hour, 50, 60, 50, 40. What's her average acceleration? That's different than average value of a function. I'm not asking for the average value of velocity. I'm asking for average value of the acceleration. And that one isn't too fancy. We've done that before. Like when I gave you a position function to find average velocity. Given position, you can find average velocity by taking change in position over change in time. But this is a velocity function, so we could take the change in velocity divided by the change in time. That would just be the slope of the green line. We could take velocity at time 7 minus velocity at time 1 divided by 7 minus 1. That's how we would answer the average acceleration question. We would take the change in velocity over change in time. So that question is even more confusing to students who learn today's lesson, because it's like, wait, average acceleration? Are they asking for average value of a function? No, if they were asking for the average value of the function, they would be asking for the average velocity over the interval 1 to 7. Now, average acceleration, that's not too tough. Just change in velocity over change in time. What would you do to find the average velocity when the velocity function is given? I mean, think about it. When in the past, in your life, when you've been asked to average things, like what's the average height of those 5 people, or the average age? You know, this person's 15, here's a 17-year-old, 16, 16, and a 12-year-old. Well, to find the average of a finite number of numbers, we just add up the numbers divided by the total number of numbers. Notice how much more difficult average velocity is. Average velocity, there's an infinite number of velocities between, let's say this is 40 miles per hour, 60. There's an infinite number of velocities in between. This is not an easy question. Do you have any ideas as to what we can do to find the average of velocity, And again, suppose we had an equation for velocity, some v of t equation, some function of t. Can you tell me what you think you would do to find the average value of this velocity function? Does this feel like a hard question?
Did you use the mean value?
Yeah, the mean value theorem for integrals, that's our lesson for, yes, you would, Adam, you would use the mean value theorem. So I want to show you what it is. In fact, let's continue with a slightly simpler diagram. It doesn't matter what the velocity function is, the concept is the same. But to make it look a little bit easier, if I wanted to find the average value of this function v of t, and by the way, v of t could be any function, doesn't have to be velocity. It could be the depth of the snow. This could be like the shape. Looks kind of like a snowdrift, right? Suppose you have a blizzard and someone asks you to find the average depth of the snow. How deep is the snow? And you're like, how am I supposed to find how deep the snow is? It's curved. It's like, what am I supposed to do? Get a bulldozer and make it all even?
Exactly.
Well, yeah, you could do that. You could get out a bulldozer or a shovel. Let's say this is O'Hare Airport, because they report the average depth of the snow at O'Hare. You could get someone to level out all the snow so it's a rectangle. What we mean by the average value of the function is the height of golf ball C. It's like this f of c is what we mean. F of c is the average depth of the snow, or the average velocity. We can actually find it by thinking of it as the width of a rectangle, and from 1 to 7, that's the length. Isn't it true? I mean, today's lesson is based on the very straightforward idea that the area of a rectangle is the length times the width. If you understand that, then the average value of the function W is just area over L. That's today's lesson. If you want to find the average value W, just take area divided by length. So, W is area divided by length. So in general, the average value of a function, or the mean value theorem for integrals, is area divided by 7 minus 1. F of c is 1 over 7 minus 1. That's like the length of the rectangle, times the area of the rectangle would be the same as the area before the bulldozer comes and levels it out, which is the integral from 1 to 7 of v of t dt. And it's a function, I have f in there. In general, let's just make it general because it applies to velocity or any other function. The function that I want you to triple box, which is really the answer to the question for the average value, f of x, the average value is 1 over b minus a times the integral from a to b of whatever the function is dx. It's area divided by length to get the width. You'll be able to see examples of that as you do the homework. It's a pretty straightforward idea, but triple box it because that is the mean value theorem for integrals, also called the average value of a function. So because we need to take student surveys today, I need to shift gears here. For the last 10 minutes, I would like you to take out your Surface and go to period 7 for AP Calculus. Go to the General Resources topic. This week, classes here at Wheaton Academy for periods 4 and 7. We're doing student surveys. So,
Yeah, W is F1.
Okay.
please, on your Surface,
Yeah.
go to Topics, click on Syllabus and General Resources. You will see the 7th period survey link. You can do 4th period, okay? So, please click on the 7th period survey. For those of you who finished early, I'm going to give you the AP Calc practice exam. I'm just going to ask that you, if you finish the survey early, just do problems 11 through 14 on the document I'm about to distribute. So, please go to the 7th period survey and actually we have 2 things. So I'm going to ask you to work on this individually. If you have any questions as to where this is, just click on the topic, go to topics. Very first topic is syllabus and general resources. You'll see a 7th period link in there. It is. This is part of your homework. Your homework is 4.7 and this one problem. So the homework is in the textbook, 4.7, and this one problem.